The ice cube in your hand is more deadly than you know. Pick up an ice cube. Go ahead, hold it in your hand. Feel how ordinary it is. Cold, sure. Wet, yes. Dangerous? You'd laugh at that. You shouldn't laugh. That thing in your hand is one of the most physically bizarre, chemically unusual, mechanically destructive, and biologically catastrophic substances that has ever existed anywhere on the surface of this planet. It has killed more people than most wars. It has moved mountains, literally moved mountains, scraped them off the face of the earth and deposited them hundreds of miles away. It has split open solid rock that had stood for 1 billion years. It has sunk the largest ships ever built in under 3 hours on the first voyage they ever made. And here is the part that should genuinely disturb you. It does all of this by breaking the rules. Ice is physically anomalous. It violates the behavior that almost every other substance on Earth follows. It is less dense as a solid than as a liquid. It conducts heat in ways that seem contradictory. Its surface behaves like no other solid surface in nature. And underneath all of that strangeness, at the quantum mechanical level, there is something even more extraordinary going on. I'm going to show you all of it. Because ice, of all the ordinary objects in your daily life, is the one that most completely destroys the comfortable idea that you understand the physical world. You do not understand ice. Nobody fully does. And that is exactly why it is so dangerous. The rule ice breaks. Why everything else shrinks, but ice expands. Let me start with the first and most fundamental way that ice is dangerous, and that is the way it breaks the most basic rule of matter that you were ever taught. You were taught at some point in your education that matter expands when it heats up and contracts when it cools down. This is presented as a universal fact of nature, as reliable as the sunrise. Hot things are bigger, cold things are smaller. Heat a metal rod and it gets longer. Cool a gas and it shrinks. This rule underlies engineering, manufacturing, construction, metallurgy. Bridges are designed to accommodate thermal expansion. Train tracks have gaps between sections for the same reason. The rule is real, it is reliable, and it applies to nearly everything. Nearly everything. Not water. Water, as it cools from room temperature down to about 4 degrees Celsius, behaves exactly as you'd expect it contracts. It gets denser. It becomes a smaller volume for the same mass. Standard, normal, boring. And then, at 4 degrees Celsius, something extraordinary happens. The water reaches its maximum density. And as it cools further from 4 degrees towards zero, it starts to expand. It gets less dense. It takes up more volume as it gets colder. It is doing the opposite of what almost everything else in the universe does. And when it actually freezes, when it crosses the phase transition at 0 degrees, it expands by about 9%. 9%. That is not a small number. That is an enormous number for a phase transition. And that 9% expansion is the source of a staggering amount of the danger that ice poses. To understand why this happens, you have to understand the molecular structure of water. A water molecule is 2 hydrogen atoms bonded to 1 oxygen atom. And it is not a straight molecule. The bond angle is about 104.5 degrees, which gives it a bent V-shaped geometry. And this bent geometry, combined with the fact that oxygen is highly electronegative, makes the water molecule a dipole. One end of the molecule is slightly negative, the other end slightly positive. This means water molecules attract each other. The slightly positive end of one molecule is attracted to the slightly negative end of another. These attractions are called hydrogen bonds, and each water molecule can form up to 4 hydrogen bonds with its neighbors. In liquid water, these hydrogen bonds are constantly forming and breaking. The average lifetime of a hydrogen bond in liquid water is about 1 to 20 picoseconds. But as water cools and approaches 0 degrees, the hydrogen bonds arrange themselves into the most stable configuration they can find, the hexagonal lattice, the crystal structure we call ice. And that hexagonal lattice is more open, more spread out, less dense than liquid water. This is why ice floats, and this is why it is so dangerous. 25,000 pounds per square inches. How ice splits granite and destroys civilizations. When water gets into a crack, any crack, a hairline fracture in a rock, a tiny gap in a concrete foundation, a small void in a pipe wall, and then freezes, it expands by 9%. In an enclosed space, that 9% expansion generates an enormous pressure. When I say enormous, I mean it precisely. Water expanding in a sealed container upon freezing can generate pressures of up to 25,000 pounds per square inch. For comparison, a car tire is inflated to about 30 to 35 pounds per square inch. A hydraulic car jack operates at around 700 to 3,000 pounds per square inch. Freezing water in a confined space can reach 25,000. That pressure is sufficient to crack granite, not chip it, not scratch it, crack it. Solid granite, which requires a substantial explosive charge to break in normal engineering applications, can be split apart by water freezing in a small crack. This is called frost wedging, and it is one of the primary mechanisms of physical weathering, the process by which solid rock is broken down into smaller pieces over geological timescales. The Himalayas, the Alps, the Rockies, the jagged, sharp profiles of mountain ranges in cold climates are created and maintained largely by frost weathering. The smooth, rounded profiles of mountains in tropical climates, where freezing is rare, reflect the absence of this mechanical destruction. Ice is literally sculpting the surface of the earth, continuously, right now, wherever water can penetrate rock and temperatures cycle around freezing. And what it does to rock, it also does to concrete, to asphalt, to brick, to stone buildings. Every building in a cold climate is in a constant, slow war with ice. The cracks you see in old stone walls, in sidewalks, in roads, ice did most of that. The United States spends tens of billions of dollars per year repairing infrastructure damaged primarily by ice expansion. And in pipes, the consequences are catastrophic. When water in a pipe freezes, it expands. And if the pipe cannot accommodate that expansion, the pipe bursts. In the 2021 Texas winter storm, burst pipes from an unusual severe freeze caused an estimated $18 billion in property damage in Texas alone, in a single weather event from ice expansion in pipes. And I haven't even gotten to the biological dangers yet. Ice in biological tissue is another story entirely, and it is a deeply disturbing one. Because when ice forms inside living cells, the 9% expansion doesn't crack stone, it ruptures cell membranes. It tears apart the microscopic machinery of life. Ice is a cell murderer, what freezing does inside your body. Every living cell is, at its core, a membrane-enclosed bag of water. The cell membrane is extraordinarily thin, about 7 to 10 nanometers thick, which is roughly 1/10,000th the width of a human hair. It is a double layer of lipid molecules with proteins embedded in it, and it performs a staggering number of functions, maintaining the internal chemical environment of the cell, controlling what enters and exits, generating electrical signals, facilitating chemical reactions. It is the boundary between life and not life at the cellular level. When ice forms inside a cell, that 9% expansion is immediately catastrophic. The ice crystal physically punctures the membrane. It does not damage it in some recoverable way. It perforates it, rips through it, destroys the barrier that makes the cell a functional unit. And when the membrane is breached, the contents of the cell spill into the extracellular space, and the cell dies. Not is stressed, not is compromised, dies. Immediately, irreversibly. This is frostbite. When skin tissue is exposed to temperatures below freezing, water in and around cells begins to crystallize. The ice crystals grow, expanding by 9% as they form, puncturing membranes, destroying cells, rupturing the tiny blood vessels called capillaries that supply oxygen to the tissue. At the cellular level, frostbite is a mass murder of cells by ice crystals, happening simultaneously across millions of cells in the affected tissue. The damage is worse, not always during the freezing itself, but during the thawing. When frozen tissue is rewarmed, the destroyed cell membranes allow cellular contents to flood into the surrounding tissue, triggering a powerful inflammatory response. White blood cells rush in, attempting to clean up the cellular debris, and in doing so, they release inflammatory mediators that cause further tissue damage. The blood vessels, their walls weakened by the ice damage, can rupture as blood flow returns to the thawing tissue. Blisters form as the body tries to isolate the damage. There is another mechanism that is subtler but equally devastating: osmotic stress. When ice begins to form outside cells, the concentration of solutes in the extracellular fluid increases because pure water is being extracted into the ice crystal while solutes remain in the unfrozen liquid. This creates an osmotic gradient. The extracellular fluid becomes more concentrated than the fluid inside the cells, and water flows out of the cells, dehydrating them. The concentration of solutes inside the cells rises, and high intracellular solute concentrations are toxic. They denature proteins, disrupt enzymatic reactions, damage DNA. This osmotic stress can kill cells even without any ice ever forming inside them. This is, in fact, the primary mechanism by which cold-tolerant organisms like the wood frog survive sub-zero temperatures. The wood frog accumulates massive concentrations of glucose in its cells before winter concentrations so high that the intracellular fluid becomes antifreeze-like and allows extracellular ice formation to occur while protecting the cell interiors. It is a precisely engineered survival strategy, evolved over millions of years, specifically to survive what ice does to biological tissue. Most animals have not evolved this ability. For most mammals, including humans, the formation of ice in tissue is simply lethal. Napoleon's army, WWI trenches, and death by frozen tissue. Frostbite is one of the most common serious injuries in cold weather mountaineering, in warfare, in cold climates, in homeless populations exposed to winter temperatures. In World War I, more French and German soldiers were incapacitated by frostbite during the winters in the trenches than by enemy fire in some period. In the Napoleonic retreat from Moscow in 1812, frostbite was one of the primary causes of the catastrophic losses that destroyed the Grande Armée. Hundreds of thousands of men killed or incapacitated, in significant part, by ice forming in their cells. In severe frostbite, the tissue does not recover. The dead cells are not replaced quickly enough, the blood supply is interrupted too completely, and the tissue undergoes necrosis. It becomes gangrenous, black, dead. In the worst cases, amputation is the only option. Ice, forming inside living tissue, can require the surgical removal of fingers, toes, hands, feet, ears, and noses. Now, I want to be precise about the temperature at which tissue actually freezes, because it is both important and commonly misunderstood. Biological fluids contain dissolved solutes, salts, sugars, proteins that depress the freezing point. Blood plasma freezes at about minus 0.5 degrees rather than 0. So tissue doesn't actually freeze until it is well below 0. But exposed skin in severe cold can reach well below minus 10 or even minus 20 degrees Celsius. And at those temperatures, the freezing point depression is irrelevant. The tissue freezes thoroughly and rapidly. At minus 10 degrees Celsius, exposed skin can begin to show signs of frostbite within 30 minutes. At minus 40, frostbite can occur in a matter of minutes on exposed skin. Wind chill makes everything worse. When wind moves air across your skin, it continually replaces the thin layer of air your body has warmed with fresh, cold air. The rate of heat loss increases dramatically. A temperature of minus 20 degrees Celsius with a wind speed of 50 kilometers per hour creates a wind chill of roughly minus 37 degrees Celsius. Severe frostbite can occur in less than 10 minutes on exposed skin. Not because the temperature of the air is minus 37, it isn't, but because the rate of heat loss from exposed skin is equivalent to what would occur at minus 37 inches still air. And underneath all of this biological danger is the simple, relentless physics of that 9% expansion, water becoming ice, becoming larger, becoming lethal. The same expansion that cracks granite and bursts pipes is tearing apart the cell membranes of every soldier who ever froze to death in a trench. The same physics, the same 9%, operating at every scale, from rock to cell, with complete indifference. The Titanic, sunk by 1.2 square meters of hull damage. On April 14th, 1912, at 11:40 p.m. ship's time, the largest and most technologically sophisticated ocean liner ever built struck a mass of ice in the North Atlantic Ocean and sank in approximately 2 hours and 40 minutes. 1,517 people died. The ship was the RMS Titanic, and its destruction was accomplished almost entirely by a relatively modest piece of frozen water. I want to be precise about what actually happened to the Titanic, because the popular account is somewhat misleading. The iceberg did not simply smash a hole in the hull. The damage was more subtle and in some ways more disturbing. The Titanic's hull was constructed of steel plates, each about an inch thick, riveted together. The iceberg struck the starboard side at about a 30-degree angle, a glancing blow, not a head-on collision. As the side of the ship scraped along the submerged portion of the berg, the impact buckled and separated the steel plates along a total length of about 90 meters, opening gaps or popped rivets across 6 of the ship's 16 watertight compartments. The total area of the openings was estimated at only about 1.1 to 1.2 square meters smaller than a standard door. That's it. 1.2 square meters of hull damage, and it killed 1,517 people. Why? Because the ship's pumps could not remove water as fast as it entered. The Titanic could float with up to 4 of its 16 watertight compartments flooded. 5 were compromised. With 5 flooded compartments, the bow sank lower, allowing water to pour over the tops of the watertight bulkheads, which extended only to E deck, not the full height of the ship, flooding the next compartment, then the next, in a progressive cascade. The physics here are merciless and simple. Water is heavy. 1 cubic meter of seawater weighs about 1,025 kilograms. As water poured in through those 1.2 square meters at a rate the pumps couldn't handle, the mass of water accumulating in the bow steadily exceeded the buoyancy of the bow, and the ship tilted forward, accelerating the flooding. The end was inevitable from the moment those 5 compartments were compromised. And what compromised them? Ice. Specifically, ice that floats, floating, as it does, because of that 9% expansion that makes it less dense than the water it forms from. An iceberg floats with about 90% of its volume below the water surface. The portion that struck the Titanic was largely invisible, a submerged shelf of ice extending from the base of the visible berg. The danger was hidden. The danger was always hidden. Sea ice crushes ships and glaciers, move mountains. Sea ice, the ice that forms on the surface of the ocean in polar regions, is in many ways more insidious than icebergs. Unlike icebergs, sea ice forms directly from the freezing of seawater and can form a continuous sheet, meters thick, covering hundreds of thousands of square kilometers. And sea ice can crush a ship. When a ship becomes icebound, trapped in sea ice that is frozen around it, the ice can exert lateral pressure on the hull from all sides as the ice sheet moves, expands, and shifts. Sea ice can exert pressures of several hundred tons per square meter on a ship's hull. Steel hulls, not specifically designed for ice-breaking operations, can be literally crushed. The hull plates buckle inward. The ship loses structural integrity, and if the pressure is great enough, the ship sinks. Ernest Shackleton's Antarctic expedition of 1914 to 1916 illustrates this perfectly. His ship, the Endurance, became trapped in the sea ice of the Weddell Sea in January 1915 and was slowly crushed over 10 months as the ice shifted and pressed on the hull. The ship sank in November 1915 after the ice finally collapsed the hull entirely. Shackleton and his 27 men survived only through one of the most extraordinary feats of navigation and endurance in the history of exploration. But let me go further back to the ice that reshapes continents. At the peak of the last ice age, approximately 20,000 years ago, the Laurentide ice sheet covered nearly all of Canada and extended south into the United States as far as Long Island, New York, and the Ohio River valleys. The ice was in some places more than 3 kilometers thick, pressing down with a weight of roughly 27 million tons per square kilometer. That pressure was sufficient to depress the crust of the earth by hundreds of meters. As the ice advanced, it ground and abraded the bedrock below, incorporating rock fragments from fine clay particles to boulders, the size of houses acting as a colossal sheet of sandpaper. The result is called glacial striation long, parallel scratches in solid rock recording the direction of ice movement. These striations are visible today, thousands of years after the ice retreated, on exposed bedrock surfaces throughout Canada and northern Europe. The landscape of New England, the Great Lakes region, and much of the Midwest was sculpted almost entirely by glacial ice. The Great Lakes themselves are glacial features, basins gouged by the ice and subsequently filled with meltwater as the ice retreated. Ice built those lakes. Ice shaped entire continents, and it is the same ice, the same 9% expansion, the same hexagonal crystal, the same hydrogen bonds operating at a scale of trillions of tons instead of a single ice cube. Why ice is slippery science got it wrong for 150 years. Ice is slippery. You know this. Everyone knows this. But here is the question almost nobody has a good answer to. Why? What is physically happening at the surface of ice that makes it so extraordinarily low in friction? The standard answer you will find in most popular accounts and even in some older physics textbooks is that ice is slippery because of pressure melting. The idea is that when you stand on ice, the pressure of your weight reduces the melting point of the ice just below your foot, causing a thin layer to melt. You then slide on this thin liquid layer, which is nearly frictionless. This explanation sounds plausible. It has been repeated for over a century, and it is almost entirely wrong. The problem is quantitative. The melting point of ice decreases by about 0.0075 degrees Celsius per atmosphere of additional pressure. A 70 kilogram person standing on a skate blade with a contact area of about 1 square centimeter exerts a pressure of about 70 atmospheres above atmospheric. That would reduce the melting point by about 0.5 degrees Celsius, enough to cause melting only if the ice is already very close to 0 degrees. Completely insufficient if the ice is even a few degrees below 0. Ice rinks are kept at temperatures around -5 to -9 degrees Celsius. At those temperatures, pressure melting cannot happen under a skate blade. The pressure required to reduce the melting point by 5 degrees would be about 700 atmospheres, equivalent to standing on an ice rink with a steel pin about 1 millimeter in diameter. This is not what skates do. Yet ice at -5 degrees is slippery, noticeably, dangerously slippery. So pressure melting cannot be the explanation. A second popular explanation is frictional, melting that friction generates heat, which melts a thin layer of water that you then slide on. This plays a role in skating, but it doesn't explain why static ice, ice that nothing is sliding over, is still slippery. If you place your foot on a stationary piece of ice and try to stand still, you still slide. No friction has been generated yet. The real explanation turns out to be more interesting. And it was first noticed not by a modern physicist, but by Michael Faraday in the 1850s. 1 million ER visits per year, the physics of falling on ice. Faraday noticed that 2 pieces of ice pressed together would fuse, which wouldn't happen if the surfaces were pure solid. He proposed that ice must have a liquid-like layer on its surface. But it wasn't until the 20th century that this surface pre-melting could be experimentally confirmed and studied in detail. What happens at the surface of ice is this. The molecules at the very surface of an ice crystal are in a different situation from those in the interior. In the interior, each water molecule is fully hydrogen bonded to its neighbors. In the crystal lattice, 4 hydrogen bond partners, stable and rigid. But at the surface, the molecules have some of their potential hydrogen bonds satisfied by the crystal below and neighbors on either side, but no partners above them. They face air. This makes them less constrained with more freedom to move. The surface molecules exist in a state intermediate between solid and liquid, a quasi-liquid layer, sometimes called a pre-melting layer. The thickness of this layer depends on temperature. Close to 0 degrees, it can be tens of nanometers thick. At -10 degrees, a few nanometers. At -35, only a fraction of a nanometer. And at very low temperatures, well below -100 degrees, it essentially disappears. This thickness dependence is exactly what we observe in the friction behavior of ice. Ice is very slippery near 0 degrees. Less slippery at -10, significantly less slippery at -30, and at temperatures of -40 or colder, ice is actually not particularly slippery at all. It has substantial friction. This is why polar explorers can gain traction on very cold ice. Near 0 degrees, the quasi-liquid layer is thick enough to act as a lubricant. The apparent friction coefficient of ice near 0 degrees can be as low as 0.02 to 0.05. For comparison, the friction coefficient of a tire on dry pavement is about 0.7 to 0.8. Ice near 0 degrees is 15 to 40 times less frictional than dry pavement. And this is why falls on ice are so deadly. In the United States, falls on ice and snow cause approximately 1 million emergency room visits every year. They are among the most common causes of traumatic brain injury, hip fracture, wrist fracture, and spinal injury in cold climates. Elderly people are particularly vulnerable. A hip fracture from an ice fall in an elderly person has a mortality rate of 20 to 30% within 1 year. A slip on ice goes from initial foot contact to the point of no return in under 100 milliseconds faster than the human nervous system can react. There is no time to catch yourself. And because ice is hard, solid crystalline water with no give, the impact is sharp and unyielding. The combination of extraordinary low friction leading to fast, unexpected falls onto a hard, unforgiving surface makes ice one of the most dangerous surfaces the human body routinely encounters. The paradox, ice, is also the reason life exists on Earth. Now I want to talk about the paradox at the heart of ice, the fact that this extraordinarily dangerous substance is also one of the primary reasons life on Earth exists at all. Because ice is not only a destroyer, ice is, in a very specific and physical sense, the reason the oceans are not frozen solid, and the reason aquatic life survived through hundreds of millions of years of ice ages. And this too comes from that same anomaly, the fact that ice floats. Consider what would happen if ice sank. If ice were denser than liquid water, as almost every other solid is denser than its corresponding liquid, then when a lake or ocean began to freeze, the ice formed at the surface would sink. It would fall to the bottom. The next layer of ice would form at the surface and also sink. The body of water would freeze from the bottom up. In this alternate universe, a lake freezing in winter would accumulate ice on the bottom. The surface water, cooled by the cold air, would freeze, sink, and be replaced by warmer water from below, which would then be exposed to the cold air, cool, freeze, and sink again. The process would continue until the entire lake was frozen solid. Once frozen solid, the lake would not easily thaw in summer. The surface water would warm and melt, but the ice on the bottom would be insulated from the warm surface by the liquid water above. Deep lakes in cold climates might never thaw completely. Over geological time, in a world where ice sinks, the deep oceans would accumulate ice at their bottoms. More and more water would be locked up. The oceans would get shallower and eventually might freeze solid, a scenario sometimes called snowball Earth. Aquatic life would be annihilated. But ice floats. When a lake freezes, the ice stays at the surface, forming an insulating layer between the cold air above and the liquid water below. Ice has a thermal conductivity of about 2.2 watts per meter per Kelvin. It slows the loss of heat from the liquid water below dramatically. As the ice gets thicker, it becomes an even better insulator, and the rate of further freezing slows. Most lakes, even in very cold climates, do not freeze to the bottom. The liquid water under the ice remains near 4 degrees Celsius, the temperature of maximum density. Fish, invertebrates, microorganisms, all can survive through an Arctic winter in the liquid water beneath the ice, protected from the lethal cold above by the insulating ice cap. Earth has undergone multiple ice ages, the most recent lasting from about 2.6 million years ago to about 11,700 years ago. During peak glaciations, ice sheets covered much of the northern hemisphere. Yet life survived. Mammals evolved and diversified enormously. Early humans evolved, spread across the globe, and developed technology. The floating ice served as a giant insulating blanket for the ocean. It prevented total freezing. It kept the liquid water below at temperatures that life could survive. The same property that makes ice dangerous, the 9% expansion, is also the property that made life on this planet possible. 17 forms of ice, from your freezer to alien planets. Now, let me talk about something that completely shatters the idea that ice is a simple, single substance. Because the ice in your freezer, ordinary ice, ice ich, the hexagonal crystal, is not the only form of ice. It is simply the form that is stable at atmospheric pressure near 0 degrees Celsius. When you change the pressure and temperature, water can freeze into completely different crystal structures with different properties, different densities, different bond geometries. There are at least 17 confirmed distinct crystalline phases of water ice, each with its own crystal structure and physical properties. 17. A substance you use to cool drinks can exist in 17 different solid forms. Ice 6, for example, is stable at pressures above about 6,000 atmospheres. It is denser than liquid water. It sinks, not floats. Ice 7 is stable above about 30,000 atmospheres and remains solid at temperatures above 300 degrees Celsius. Boiling temperature water can freeze if the pressure is high enough. Ice X, the highest pressure confirmed form, is stable above roughly 700,000 atmospheres and is thought to have a completely symmetric crystal structure where the hydrogen atoms sit exactly between the oxygen atoms, rather than closer to one oxygen than the other. This matters because in the interiors of large icy planets and moons where pressures reach millions of atmospheres, ice exists in exotic high-pressure phases that are denser than liquid water, that have entirely different properties from the ice on Earth, and that behave in ways completely counterintuitive to our experience. The interiors of Uranus and Neptune are believed to contain vast layers of superionic ice, a phase in which the oxygen atoms form a solid crystal lattice, while the hydrogen atoms move freely through it like a liquid or even a plasma conducting electricity. It is simultaneously solid and liquid. The hydrogen atoms flow like a liquid through a rigid oxygen crystal. This is not science fiction. This is the physics of water under extreme pressure. And we have confirmed it in the laboratory. Superionic ice and the quantum physics inside. Every ice cube. In 2019, researchers at Lawrence Livermore National Laboratory created superionic ice in the laboratory by simultaneously compressing and heating water to extreme conditions and directly measured its electrical conductivity and X-ray diffraction pattern, confirming the theoretical prediction. The conductivity was enormous, comparable to that of a liquid metal. Ice conducting electricity like metal. At temperatures above 2,000 degrees Celsius, at pressures of 1 to 4 million atmospheres. Now let me come back to ordinary ice, the ice in your freezer, and tell you something about it at the quantum mechanical level that is genuinely and deeply strange. The hydrogen bond in water is not fully classical. At the quantum mechanical level, the hydrogen atom in a hydrogen bond is not a classical particle sitting at a fixed position. It is a quantum particle described by a wave function, and that wave function has non-zero probability of the hydrogen atom being found not where it should be classically, but in other positions. Specifically, the hydrogen atom has some probability of tunneling, passing through the energy barrier between two positions and ending up on the other side. This is called proton tunneling, and it happens in every hydrogen bond in every piece of ice on Earth. Proton tunneling is not a negligible effect. It affects the dynamics of the ice crystal, its specific heat, its thermal conductivity, its dielectric properties. Isotopically, ice made with heavy water, where the hydrogen atoms are replaced with deuterium, which is twice as heavy and tunnels much less readily, has measurably different physical properties. The freezing point of heavy water is 3.82 degrees rather than 0 degrees. Its density maximum is at 11.6 degrees rather than 4 degrees. These differences come directly from the quantum mechanical tunneling behavior of the hydrogen atom. The macroscopic measurable properties of ice trace back to a quantum mechanical effect happening at the level of individual protons, the slipperiness of the ice on a winter sidewalk, the fall that sends someone to the emergency room, the hip fracture that costs an elderly person their independence traces back through a chain of physical causation, to quantum mechanical tunneling of individual protons in hydrogen bonds. Ice seems simple. It is the solid form of the most common liquid on the surface of the Earth. Children make it in the freezer. You put it in drinks. But every piece of apparently simple physics conceals extraordinary depth. The slipperiness of ice conceals an unsolved problem in surface physics that took 150 years from Faraday's first observation to a reasonably complete theoretical understanding. The floating of ice conceals a molecular scale anomaly that has enormous consequences for the habitability of the Earth. The 17 crystal phases of ice conceal exotic states of matter that exist in the interiors of planets we have not yet visited. The ordinary is not ordinary. The world is not boring. The world is not fully understood. Any way you look at anything, from the most exotic subatomic particle to the ice cube in your glass, there is depth. There is strangeness. There is physics that will surprise you if you are willing to look carefully and ask the right questions. Pick up an ice cube. Look at it. Really look at it. You are holding a quantum mechanical anomaly. You are holding a substance that defies the standard rules of density and has 17 crystal phases. You are holding the material that carved the Great Lakes, sank the Titanic, protected the oceans through ice ages, kills cells by ripping their membranes, and lurks on sidewalks waiting to send people to emergency rooms. You are holding one of the most dangerous and extraordinary substances on Earth. And the most disturbing thing about it is how completely normal it looks. That is what ice teaches, if you are willing to learn it.